Okie dokie. So today we're going to be taking our sequences and adding them up. Okay, and finding series. Okay, finding the sum of an infinite number of things and seeing if that sum converges to a certain value or diverges. Okay, and this is going to be the majority of our the majority of this unit, I guess, is going to be focused on these infinite sums, okay, known as a series, and kind of seeing how we can evaluate these things. Okay, we'll be developing like a series of like a group of tests, okay, to kind of help us evaluate these. Sometimes the best we'll be able to do, sometimes the test will be able to tell us is that it converges or diverges, but it won't tell us exactly what it converges to. Sometimes, we won't be sure about, So anyway, we're going to develop, like, again, some tests. Kind of like we do with, like, I guess, integrals in a way, where we had, like, well, here's a thing. Can we even evaluate this thing? And if so, what rule would you use to evaluate and stuff like that. So it's kind of similar to that, okay? So one important application of infinite sequences, right, which is a list of numbers, is the representation of infinite summations. Okay, the sum of an infinite sequence is an infinite series. Okay, I know it's going to be really confusing because both of these things start with S, sequence and series. We tend to talk about these things in relatively the same breath in mathematics. Okay, sequence is a list of numbers, series is a sum of numbers. Okay, so you can see here our traditional sequence. Okay, in a sequence, these would be separated by commas, right? But since we have a sum now, it's represented by this notation here, the sigma notation. And I want to kind of like zoom in on that just to make sure we're comfortable with this, because I know in pre-calculus this was an uncomfortable topic. Okay, but you can see here that we have this Greek letter. It's the capital sigma. Okay, capital sigma. It's that makes the S sound in Greek. All right, if you go to Greece or whatever, you'll see this letter used. It's like it's a thing. And the values here, okay, these are kind of like our counters, right? So we start with n equals 1, all right, and we count up to infinity. So that means we're going to be counting up an infinite number of these terms, okay? So it starts at n equals 1, so that's where you get the a sub 1, and then we'll add up a2, a3, a4, blah, 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 all up to a sub n, and then, a sub infinity, I guess, kind of thing. You're just going to add all those up. Okay, so that's the idea of sigma notation. There's just a short way to write a sum of an infinite number of things, or a finite number of things too. It doesn't have to be adding up to infinity. You could put a 10 here or a 20, and add up just the first 20 terms, the first 10 terms, or whatever kind of thing. All right, anywho, to find the sum of an infinite series, okay, which is like the limit, okay, we examine the sequence of partial sums. Okay, so we take a look at kind of like the kind of like a sequence, okay, a list of their partial sums, and see if there's like a format or a pattern to those partial sums. Okay. So again, we're going to consider this series here, all right, and let's kind of write this in sigma notation. So it looks like we're adding up an infinite number of things, right, with a dot 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 a sub n there. So we'll sum from n equals 1 to infinity. Where you start, by the way, here, so sometimes you'll see our sums starting at n equals 0. Sometimes you'll see our sums starting at n equals 1. Where you start here is more a matter of what kind of is more comfortable for you, or what makes the most sense, I guess. It's kind of, it's up to you sometimes to decide whether you want to start at 1 or 0, whatever kind of makes the most sense to you here. In this case, right, we see that, okay, well, 1/2 to 1/4 to 1/8 to 1/16 to 1/32, 1/32, we see that the 1s in the numerator aren't changing, so we can just put a 1 in the numerator. And then what's happening in our denominator here? What would be the rule for that? So, say it again. 2 to the n, 2 to the n, 2 to the n, 2 to the power of n. Exactly right. Okay? And this is exactly what we need, right? If I put a 1 in for the first term, I get 1/2, right? 1 over 2 to the 1. If I put a 2 in for the second term, 1 over 2 to the 2. And so we can see that that's exactly our pattern there. Or if I write it a slightly different way, right? I could also say the quantity 1/2 to the n power, right? Those are saying the same thing, because 1 to the n would still be just 1, 2 to the n would still be 2 to the n there. So one of those two ways there. Okay. And so what we're going to do is then examine this kind of sum. Okay, we're going to examine this, the partial sums, I should say. Okay, so the sum of the first term is called the first partial sum. Okay, so it's just like the sum of the very first term, which is not really a sum, it's just that's what it is, right? The second partial sum is the sum of the first two terms. The nth partial sum is the sum of the first n terms. So you can kind of think of this partial sum idea as almost like the factorial is to multiplication, the partial sum is to addition, right? We're going to add up all the kind of like the terms before, before it for whatever those nth partial sums are. So here for the first term, right? Okay, there's our first partial sum. Right here, it's just the first term. Okay, and then we'll do the second partial sum here kind of on our own, and I'll stop writing these after a while because it's just going to be too much, but you get the idea. Okay, so that's going to be 1/2 plus what else? 1/4, right? We're just adding the second term there too. Okay, 1/2, well that's 2/4 plus 1/4, so we get 3/4, right? And then for the third partial sum, and this is the last one, all right here. Third partial sum. Okay, well that's going to be 1/2 plus 1/4 plus 1/8, right? Okay, so we're just adding on that third term now. 1/2 plus 1/4 plus 1/8, and that's equal to, okay, so 1/2, that's 4/8. 1/4 is 2/8, so we have 6/8, and then plus another 8, 7/8. Okay, and then we'll do the same thing here. For the first four terms, that's 1/2 plus 1/4 plus 1/8 plus 1/16. Okay, and this is going to be what? What's this sum? 15/16. Exactly right. Say again? Third partial sum is 7/8. Yeah, sorry, I can zoom out one more. There we go. Fit it all in there. Okay, and then we'll do the fifth partial sum here. So let's see that. So, well, anyone want to guess what that one's going to be? 30 seconds. You got it. Okay, so clearly, right, you can see this is the idea behind this, right? So rather than trying to take, or one strategy here we can use is rather than trying to take the entire infinite sum of these things and just kind of like add them all up, if we start looking at the first partial sum, second partial sum, third partial sum, and we can see a pattern develop as we proceed through those partial sums, right? Okay, how can we write then this general sum to the nth, or the nth partial sum here? What's the formula behind that then? Okay, well, let's look at our denominators, right? 2 goes to 4, goes to 8, goes to 16, goes to 32. So what will the denominator of the nth partial sum be? Not n squared. 2 to the n. Yeah, 2 to the n. Yeah, 2 to the n. Okay? And then what will the numerator for our nth partial sum be? 2 to the n minus 1. Exactly right. It's like the denominator, but take away 1. All right. So we started talking about sequences, right, very early on at the start of this unit. We then now are talking about series, okay? But to evaluate the series, which is the sum of these terms, we go back to the idea of a sequence, all right? This is a 1/2, comma, 3/4, comma, 7/8, comma, 15/16, comma, 31/32, comma, and you could keep doing that sequence, okay? So this is like almost a sequence in itself right here, and so we get this, and we have this formula then for any of the nth partial sums. But of course, we want to know what happens as we go to infinity. So we're going to figure out the limit as n approaches infinity of this sum, which is merely the limit as n approaches infinity of this nth partial sum formula here. Okay? Because we want to know what happens as you go out to infinity, right? What happens as you start adding these things up? Infinite nth partial, or infinite partial sum, I guess, kind of thing, or the full sum, I guess we'll say. Well, if I plug in infinity here, what's my numerator going to be? Infinity. And what's my denominator going to be if I plug in infinity? Infinity as well. And so that's indeterminate form, so we can do what? Apply L'Hopital's. And this one will actually work for. Thank you, Mark. Good boy. Okay, this one, it will actually work if we take L'Hopital's here. So again, we haven't seen that derivative of 2 to the n. We did see it yesterday, though, so hopefully it's still fresh in your memory. What is the derivative of 2 to the n?
2 to the n times the natural n.
Very good. Yes, 2 to the n times the natural log of 2. Okay, so 2 to the n times natural log of 2. And then the denominator is going to be the same exact thing, 2 to the n times the natural log of 2. What happens with these terms? They exactly cancel, and we're left with 1. Well, the limit as n approaches infinity of 1, it's still 1. Okay, so it all just cancels, and we're left with just a 1. Okay. So kind of, let that sink in. We're adding up an infinite number of things. We're starting with 1/2, and then we're adding 1/4, and then we're adding 1/8, and then we're adding 1/16, 1/32, all that stuff. And eventually, it'll all those things, those infinite terms will add up to 1. Go ahead, Gabe.
I was just going to say, how did you know that it was going to be 1/2? Or how you're adding 1/2 each time, I guess. Or multiplying by it. Or to add 1/4, 1/8, 1/16. But it was just the equation above, right?
Exactly. Yeah, all of this is developed from this kind of we're just investigating this first, this kind of, this infinite sum right here first. And we're doing it by looking at their partial sums, getting a pattern for that, and then using that pattern to go to infinity kind of thing. Does that make sense now? Yeah. Okay. So, definitions of convergent and divergent series. So, of course, we would say then this series would what? Converge or diverge? Converge, right? Because it goes to a number. Okay. So, if the sequence, so again, this is, we're jumping back and forth between ideas here, right? If the sequence of partial sums, okay, s sub n converges to s, some number, like here we converge to 1, then the infinite series, sum from 1 to infinity of a sub n, also converges, okay, and it has a sum s. Okay, so we're using the partial sums in a list, that is a sequence, to help determine if the series converges, okay? And then if the sequence s sub n diverges, then the series will also diverge, okay? So if we did this limit here for our formula that we had, if that formula kind of diverged, then we would expect the series to also diverge as well. But since it converged, then we can say the series will also converge. Okay? So questions on any of that? It's like subtleties here, kind of jumping in and out of some two close related ideas. Did you have a question, Sean, or are you just stretching?
How many repetitions of the partial sum do you have to have in order to just confidently say that, confidently analyze things?
Right. That's a good point. That's a good question. I mean, I think I'm gonna say the question really depends. I think it's something we'll kind of develop as we go here. I think certainly after 5 terms, I think we got the point. It seems like I feel like 5 terms maybe is like the magic number. No more than 5 terms, I would say. If you feel like you can do it in less than that, feel free. But I'd say no more than 5 terms, I would say. But that's a good point because of course this can be a little bit of work otherwise. So. All right, so let's turn the page here. Okay, so our directions here are having us do kind of 2 things for each of these. So first it says determine if the sequence a sub n converges. Okay, notice this is not sequence of partial sums. This is just the sequence of a sub n. Just determines if that converges. Okay, then we're going to determine if the series, which we are given here, okay, converges. Okay, and you'll notice here the series is described as the sum from 1 to infinity of a sub n. Okay, so let's do that here. I'm going to split this up. I'll do, I'll do this first one here, and then I think, yeah, we'll maybe have you guys try the other one here. Well, yeah, we'll see. Okay, so first we'll do the sequence, just because that's what the directions ask for first. So we'll say the sequence. Okay, and I'll zoom in here some. There we can do that. Okay. So what is the sequence here that we're evaluating, that we're talking about? Yeah, it's 1/2, right? A sub n, right? We were just told here the series is described this way. A sub n is next to the sigma there, and so this a sub n also is just 1/2. So in other words, our sequence here is equal to 1/2. So in other words, what's our list of numbers in that sequence? The first one will be 1/2. The next one will be 1/2 again. The next one's going to be 1/2 again, so on and so forth, right? There's no n there. There's no n that affects that 1/2, so it's just going to be 1/2, 1/2, 1/2, 1/2, so on and so forth. Kind of a boring sequence, but there it is. Okay? And we're asked to determine if this sequence converges. So we're going to do the limit as n approaches infinity of our sequence here. Okay? Which is, the limit as n approaches infinity of 1/2. And what is the limit as n approaches infinity of 1/2? 1/2. Okay? So we say our sequence converges to 1/2. The sequence a sub n converges to 1/2.
Do we have to write that?
Do you have to write that? I think for the notes, I think it's a good idea. I think it's a good idea. It's kind of like your, I don't want to say your justification sentence, but like your concluding sentence there.
So could, like, on a test, could we just write 1/2 on the convergence?
That might be okay, I think, yeah. Later it's going to be, when we're talking about like, later as we develop like more tools to help us determine when things converge or diverge, we're going to need to like name names as far as like, this converges by the blank, blank, blank test kind of thing. So you'll want to make sure that you're able to do that too. But, for right now, I think we're okay with just putting that. So, okay. So, let's talk about the series then here, okay? The same thing. So n equals 1 to infinity, and now we're going to add up the number 1/2 there. Okay, so that's 1/2 plus 1/2 plus 1/2 plus 1/2 plus dot, dot, dot. Okay? So just take a look at that series, okay, and just think in your mind whether you think it's going to converge or diverge. I'm not going to say anything just yet. Just think about what's happening, all right? Think about what we're adding up and stuff like that, and just think about whether you think that series is going to converge or diverge, okay? Just think about it, all right? I'll give you 30 seconds to think about and make sure you give it a shot. So think about what you think is going to happen. It is possible to just figure it out just by looking at it there. Okay, just kind of reason it out. Okay, converge or diverge? What do you think? This series, if we add up an infinite number of 1/2s, is that going to approach a single number, or is it going to increase or go off to infinity without bound? Go off to infinity, exactly right. This series will diverge. Okay, the series will diverge. Okay, are we all okay with that? Are we convinced that that's going to be so? Anyone not sure why that's so? Okay. If you decide that you still aren't, if you figure out that you're not convinced later, let me know. But for right now, we'll move on. So let's take a look at letter B. So why don't you guys, let's go ahead here and figure out whether this sequence converges or diverges here. So why don't you guys go ahead, come up with well, we already have the rule, so go ahead and figure this out. Tell me now. Go ahead and do the calculation that we used here to figure out whether this sequence is going to converge or diverge, okay? And so again, I'll take that a sub n. Oops. Remember, 0.1 is the same thing as 1/10, right? So. 30 more seconds here to think about whether this is going to converge or diverge. And of course, if it converges, please try to identify where it converges to, or what it converges to. Okay. Oh, Madison question. We're starting with our n equals 0. Yeah, this is different. And again, it's just, in this case, we happen to start with n equals 0 for this one, for whatever reason. But that's a good, yeah, thank you for pointing that out, though, Madison. That is a good point to make. We did start with n equals 0 as our first number here, our first counter kind of thing. So, yeah. Okay. Does it diverge or converge? Converges, and it converges to 0. Exactly right. Okay. So again, it's kind of like up to you. Some of you guys might be able to just like look at this and see, as we take our 3 and multiply repeatedly by 0.1, 0.1, 0.1, that's going to diminish the value of our, next successive term, continually on down to 0, right? Because we're multiplying by 0.1 repeatedly over and over again. So you might just be able to see, oh, it's 0, right? That's what it's going to be. If you need to see it, with a limit, though, using those limit rules and stuff like that, well, 3 times 0.1 to the n is the same thing as 3 times 1/10 to the n. 1 to the n will just be 1, so that 1 times 3 will give us a 3 in the numerator. 10 to the n will be 10 to the n, right? So make that approach infinity. That denominator is going to get ginormous. 3 is going to stay 3, right, as we go along, and so it's going to definitely approach 0, right, for sure. Okay, so again, the sequence converges to 0. Okay? So now let's see what happens when we start adding these terms up. Let's see what happens when we start adding these terms up. Okay. And I thought this was kind of neat, but you might not think so. So my apologies. I'm not going to hype it up too much. Bless you. Okay. So our first term is going to be 3, right? Then we're going to add to that 0.3, and we're going to add to that 0.03, and we're going to add to that 0.003, so on and so forth, right? So we're starting with 3, and then it's going to be 3.3, right, after that second partial sum. And after the third partial sum, 3.33. And then the fourth partial sum, 3.333. And as we continue to add, what are we going to end up with? 3.3333333. Yeah, it's 10/3. Series converges. To 10/3. Without having to do much work here. Now we'll come up with and the next, the very next thing we're looking at a geometric series. This is a geometric series, so we'll see a way to actually calculate that rather than just having to see it, because I know that can be kind of weird, right? You're like, well, will I always see this, But anyway, this one's pretty easy to see. Okay. One thing I do want to point out though here. Okay. So if we take this in total here, the sequence converges, but its series diverges. Here, the sequence converges, but the series converges, right? So you want to be careful about how you try to relate things. If a sequence converges, the series may still diverge, right? But here also, if a sequence converges, the series may converge as well, okay? We'll develop the relationship between that here as we go as well. But anyway, for right now, we'll just leave it at that, okay? The two don't necessarily guarantee the other kind of thing. But we'll see, again, a closer relationship with that later. All right, so let's talk about geometric series, okay, which is the first, kind of and that's what, I guess, well, at least this one is right here with geometric series right there, okay? So a geometric series is in the form, the sum from 0 to infinity or 1 to infinity, that's okay, of a times r to the n, okay, where a is like a constant, right, and then r is what you call the common ratio. Okay, you may remember these from pre-calculus. Remember hearing it at least from pre-calculus. Okay, right? And again, you see here with that repeated multiplication. Okay, the idea is we're repeatedly multiplying by that r value over and over and over again. So, okay. So recall from pre-calculus that an infinite geometric series converges, so again the series, which is the sum, right, converges if the absolute value of r, if your common ratio is less than 1. Okay? It diverges if the absolute value of r is greater than or equal to 1. And the sum, if it converges, right, if it converges, then the sum of the convergent series will be exactly that. The first term divided by 1 minus the common ratio, the quantity 1 minus common ratio, where a sub 1 is the first term again. Okay? So if we can identify a series as being geometric, we can then, use that formula as long as our common ratio there, the absolute value of the common ratio is less than 1. So, verify the convergence of the series from the previous example using the geometric series test. So we'll do these two right here, and then we'll also look at letter C as well, which is going to be a new one we haven't seen yet. Okay? So this, believe it or not, is a geometric series. Okay? If we go back to our series right here, what is the number that we're repeatedly multiplying by? A 1. Very good. Yes, we are multiplying by 1. Okay? So in other words, we could rewrite this as 1/2 times 1 to the n. Okay, 1/2 times 1 to the n. Okay, so that's now in like the geometric series formula. Or whatever. Never mind, I'm not going to worry about that. Okay? So, what do we know about a geometric series? It converges, right, if the absolute value of, what's our common ratio here? What's the number we're multiplying by repeatedly? 1, right? It's the 1. So if it converges if the absolute value of 1 is less than 1. Is that true? No. So, okay, it will diverge if the absolute value of 1 is greater than or equal to 1. Is that true? Yes. Okay, remember here, r is equal to 1. I'm going to put that over here. Maybe r equals 1. Okay, and so since that is true, then we know that it diverges. And there's no more work to be done, right? We only use that formula if it converges. Okay. Now let's do this one. Okay, let's do this one here with the fact that we already know what it adds up to, but let's use it to see if that actually works. Okay, so this one very clearly is a geometric sequence. Again, we have our a and our common ratio here. What are we repeatedly multiplying by? 0.1, right? R is 0.1. So the absolute value of 0.1, that is less than 1. So by the geometric series test, this series converges. I'm off the screen, sorry. There we go. I can zoom out a little bit. There we go. So get both if I need to. Okay. And so then what will its sum be? Well, the sum will be the first term. Okay? Now, here's where it gets a little bit tricky, right? Okay, I said a sub 1 was the first term. But for this, it's actually going to be a sub what? 0, right? The first term here is whatever our counter starts. So we're starting at 0. So it's actually 0 that we want to plug in here for n. Okay, it's actually 0. So we want to actually do 3 times 0.1 to the 0 over 1 minus our common ratio of 0.1. Okay, again, since that n equals 0, okay, our first term here, it's a sub 0. A sub 0 is our first term. So that's going to be 3 over 0.9, okay, which is the same thing as saying 3 over 9/10, which is the same thing as saying 30 over 9 or 10 over 3. Okay, after all that simplification and stuff like that there. Okay? Questions on any of that? So you guys go ahead and try letter C then. Okay, so give letter C a shot. Where are we going? going to Fun Town. Population, us. Oh, that cracked me up.
Oh my god.
So your common ratio here would be 1, right? Because what is it that would be repeatedly multiplied here? So this 5 is being raised to the n, or actually the 5 in the denominator is being raised to the n. So you think about this, that's like 8 times 1 over 5 to the n, or you think it as 8 times. So
Is that
we're
two?
Um, did you raise the whole thing to the 1 minus n?
Yeah, well, we can tell.
Yeah, I don't think it would be the same thing.
That's one minus two.
Right, yeah. Yeah, because, well, you can't combine it together because that's an 8, it's a different place than a 5. If they were both 5s, then you could do what you did there, that's fine, yeah. But if it's 8, you have to, yeah. I got it.
Well, what you can do is make that
So you're on the right track. Remember that 5 in the denominator,
five.
so it's actually not times 5 each time, it's really 1/5. Right, because it's 1 over the top. It's 8, so, okay, I write with my own pen here, so. Think about it like this, we'll put 8 times.
Mario, you get caught traffic.
Right, or exactly.
No, I just didn't want to go to school. My mom kind of gave me a little push to go towards school today.
Did you go in Hagerstown?
Yeah, I took on Boyers Mill and there was still an accident, so I was kind of stuck because everybody.
I don't know why they closed on Hagerstown. E4's look good. I drove with, yeah, E4's the windy way.
When I
And then
went,
they told me to turn around, I was like,
right?
Divergent, there was an accident too?
Yeah, there was an accident. There was an accident. Yeah. Yeah, as soon as I was driving by Uniontown, they had already closed it off. Like they actually had like somebody there saying you couldn't get out. And so I'm driving and then like over there by the summer field entrance. Yeah. Dude, the accident on Boyers Mill though was like bad. I'm pretty sure that someone went to go make a left-hand turn and somebody like tried running it. It was bad. Yeah, somebody was like turning from Boyers Mill to go left towards Newmarket, and somebody was like flying this way. Like,
Okay, yeah, simplify that.
it was a bad accident.
Simplify that?
that's the place now. Not the right stuff.
I don't think you simplified that accurately. What's 8 times 5?
I did it the wrong way.
You do not know the way.
Yes, that's good. Okay, right idea.
Mr. Witt set it up.
Say again? Yes, if that was your common ratio, but, see, the negative n is gonna, that's right, but let's rewrite that as
Let's see if my mom actually takes me to school.
Okay? That's your ratio. Because the ratio is going to be the positive end there. That's the speed multiplication. It's just positive.
No matter what,
Okay. All right, here we go.
sometimes
So you should have gotten this. 10.
it starts at like 6 o'clock.
Let's see if I can get there. We got the whole thing in there. Okay. Good morning, Mr. Lillard. Do you need somebody? I'm just looking for a track guy. Okay. Just gotta keep looking.
I'm your guy.
Would you stand up? I will be that man. All right. So here we go. So yeah. All right. Rewriting this 8 over 5 to the n. And again, it's helpful here, folks, if you need to consider writing out the first few terms. That can also help you identify that common ratio to see what am I multiplying by each time to get to the next, number in the series, okay? Don't feel like you have to go just from, from rewriting it alone. You can write out the first few terms if you need to help you see what is it that we're multiplying by every time there. And I think that'll be helpful too. So just consider that, okay? So anyway, your first term is going to be 8 then. Your common ratio is 1/5 or 0.2, and so you should end with 10 when you simplify there. Questions on any of that? All right, we're going to keep rolling then here. So of course, right, we did this yesterday too. We were given sequences yesterday, and then we were asked to, write those sequences out, and then we were given the list of numbers and asked to come up with a sequence that, creates it, right? Same thing here. Here we're given a series. We're asked to come up with the sigma notation for this particular series. Okay? And then we're going to determine if that series, they're all going to be geometric here, if the series is going to converge or diverge based on, again, that common ratio and stuff like that here. Okay, so we know we're going to need to use our sigma here. All right, and we're going to need to count up to infinity. And then we're also going to have to make a choice about whether we want where we want to start our counter, right? Do we want to start at 1? Do we want to start at 0? Well, maybe we can kind of see what's happening here, right? So for our numerator, it's always going to be what? 4, so we just put 4 in the numerator. That's pretty easy. Over, and then what's happening here in the denominator? We start with 3, and then it becomes 9, so we're going to multiply by 3, and we're multiplying by another 3, and multiplying by 3. So again, we see that repeated multiplication, which means we need to have what right here? 3 to the n, right? Okay, and then in order for us to guarantee we get that first term here, right, if I just say n equals 1, it's going to work out no problem, right? It gives us exactly what we need. So we're going to start at 1. It just makes sense here to use 1 because that's where, our first term, it just helps out with that way. Okay? Yep.
If it was n equals 0, would it have 4/3 twice?
If it was n equals 0, it would have 4 and then 4/3, right? Because 3 to the 0 would be 1. Mm-hmm. And again, that could be a different kind of sequence that you see too. So anyway. Okay, so there's our 4 over 3 to the n, which, again, I'm going to rewrite just like we did for the last one. N equals 1, 4 times 1/3 to the n. Okay, and so then you guys go ahead, figure out if it converges or not, and then give me the sum as well. So go ahead and take a minute there and do that. Okay, since I went ahead and rewrote it for you there. So right now, some of the difficulty that will come, okay, is that we already are given what we're supposed to do here, right? The series that it matches up with. Later, it's going to be, part of the challenge is going to be determining, what is this series? Is it geometric, or is it this other kind, or is it this other kind of thing? That's where some of the difficulty is going to come. Is just determining what we've got and how we're going to evaluate it. So right now, we're just using that same test over and over to kind of help stuff too, for convergence and divergence stuff. Okay. So, hopefully you got that it does converge, right? The common ratio here is 1/3, which its absolute value is less than 1. When you set up your formula, you get 4/3 over 1 minus 1/3. You can evaluate this different ways. Let me give you an idea here, though, that might help. Instead of actually like doing 1 minus 1/3 and then the 4/3 in the numerator like that, okay, and then getting like 2/3 and then 4/3 divided by 2/3 and doing that math, consider here multiplying the top and bottom by that denominator of 3. Okay, in the numerator that would leave us with 4. The 3 here would distribute to the 1 and the minus 1/3 to give us 3 minus 1, and that just, I don't know, maybe it's easier, maybe it's not. Maybe you don't need that to help you out there, but just a consideration. Okay, to simplify that down to be just 2. Okay, questions on letter A? All right, well, why don't you guys go ahead then, take a look at letter B and see if you can set it up. Okay, so you can get the setup for the series here. I'll give you a hint. I'm going to use I'm going to have my sum start at n equals 0 here. Okay, just to give you a little hint. Is it necessary that you do that? No, but I am going to start with n equals 0 there. Okay. Okay, so I'm going to do that. So again, go ahead, take like a minute or so, 30 seconds or a minute. Okay, and get that written out. See if you can do that. Okay, so hopefully you got something that looks like that. Okay. Questions on the setup there? Again, I use n equals 0. You could use n equals 1 here, but I think n equals 0 is the better approach, I would say. But you don't have to do it that way. So, questions on that? Okay, and so since these are all to the n power, right, the negative 1's to the n, e's to the n, 3's to the n, we can put them all together in a single kind of fraction here and say negative e over 3 to the n. Okay? What's our common ratio going to be here according to this? What are we repeatedly multiplying by? Negative e thirds. Right? Negative e over 3 is what we're going to repeatedly multiply by because that's what's being raised to the n power here. So our first term is 1, right? So you could put a 1 in front here if you wanted to, right? Not necessary, but you could. And then we're going to repeatedly multiply by negative e thirds. So we're going to take a look here. Our common ratio is negative e thirds. We're going to do the absolute value of that. Is negative e thirds less than 1? I'm off the screen, sorry. Is it? Yes, and we can do that without our calculator for sure, right? Because we know that E is approximately 2.7 something, okay? 2.7 divided by 3, 0.9, right? So it's going to be just below 1, and so we know the series will converge.
Wait, why would you use the e, not the 1?
The 1 is not repeatedly multiplied, right? It's not being raised to the n power there. What's being raised to n power? What's going to be repeatedly multiplying with each new term is going to be that negative e third.
But in your first equation, you have negative 1 to the n.
Oh, yeah, I did. I did negative 1 times e over the 3 there. That's where I got the negative e over 3 from. Yeah. Okay. And so series converges. And so again, we'll set up our formula here. The first term is 1, right? We already have that. 1 over 1 minus negative e over 3. And again, I'm going to do that whole multiplying the top and bottom by the denominator of 3 there, just to kind of make it look nicer so we don't have fractions within fractions. So 3 over, that's going to be plus positive there, so 3 over 3 plus e. And there's our sum. Which again, that's equal to the sum from 0 to infinity of negative e over 3 to the n. Okay. All right, go ahead and try that last one then. Letter C. Oh, question, Lander.
If you can write the equations in different forms, what if you get a different answer than that?
So good question, right? We can write it in different forms. So, for example, let's say we maybe chose n to be equal to 1 there instead. Like, hypothetically, would that be okay for you, something like that? Okay, so let me just show you here. So instead, if I said, like, let's have infinite, and that's actually the way I did it first, is I did n equals 1. Okay, in this case then, for our, kind of like our alternator there, that -1 is going to have to be n minus 1 then, power, okay? E will also be to the n minus 1 power, right? And then that 3 will also be to the n minus 1 power. So far so good, right? Okay, but we can still see it's going to be geometric because we are repeatedly multiplying by that -e/3 kind of thing. So you're following me so far with that? Right? And then when we go to do the actual sum, right, will it converge? Well, the first term is going to be, now we're not going to plug 0 in for the first term, we're going to plug 1 in for the first term. And so we're still going to end up with the exact same first term and then the exact same common ratio, so we'll end up with the exact same answer. Okay? So, in other words, we shouldn't get, which makes sense, we shouldn't get different answers for writing equivalent series. So, anywho. So yep, go ahead, let's write this one out here. All right, so I guess I'll do it. And for this one, I'm going to do n equals 1. I'm going to start with n equals 1. So it looks like in the denominator, we're multiplying by 3 every time. And it looks like in the numerator, we're multiplying by 4 every time. And so it looks like we're going to have 4 to the n over 3 to the n, which just is 4/3 n. Okay. And so then what can we say about this series? It diverges. Exactly right. Okay, our common ratio is greater than or equal to 1. So by the geometric series test, this series diverges. Okay, so you had to get one of those in there too, right? Show that it diverges. Okay. Let's move on down here then to example 4. Take a look at this guy. All right, so we're going to consider the geometric series. So we're already told it's a geometric series. That's nice. Okay. From n equals 1 to the sum from n equals 1 to infinity of a sub n, where a sub n is greater than 0 for all n. The first term of the series, a sub 1, is 720, and the third term, which is a sub 3, is equal to 80. Determine the convergence of the series if it does, okay? So if it does converge. So we've got this information, right? N equals 1 to infinity, the sum from n equals 1 to infinity of a sub n, and we have that that's equal to 720 plus something plus 80 plus, and then dot, dot, dot. We've got some more terms we're going to be adding on there, right? Okay. So, let's see here. Well, we know it's geometric, all right? But in order for us to figure out whether it converges or not, we need to figure out the what? We need to figure out the common ratio, right? We've got to figure out that common ratio to figure out if it converges or not, right? Is r less than 1 or is r greater than or equal to 1? Well, with this information, how can we figure out the common ratio? Do we have enough here to figure out the common ratio? Okay, we've got our first term. We don't know our second term, but we do have our third term. So normally what we would do here is see, okay, 720 times what gives us a sub 2, right? That would be like our common ratio here. This times r will give us, this number right here. And then this number times r will give us this number right here. We don't have that middle term here. Well, how many applications of the common ratio does it take to get us from 720 to 80? 2 of them, right? So it's going to be times r, which is really like r squared, right? Okay, r to the 2, right? R squared, we're doing it twice to get from that 720 to 80, okay? What would we multiply 720 by to get 80? Not 1/6? Not 1/7? Do I hear 1/9? Because that's what the actual answer is. Okay, it's 1/9. How can we figure that out? 720 times what gives us 80? It's a simple equation. What should we do to both sides here to solve for the what? Divide by 720. So that what is divide by 720, and so that simplifies to 1/9. Okay? So the idea here, right, when you're trying to figure out what, 720 times what gives me 80, it's a simple, little math equation right there. Okay? Just 720 times x equals 80, so that means x has to be 1/9. Okay? But that's from 2 applications of the common ratio there, right? And so what is r? What is the common ratio going to be? 1/3. Okay, so right away we can tell the series will. Say again? Good question. Right. So in this situation, right, we are square rooting both sides, and so it should be plus or minus 1/3. But there is some information earlier in the problem that tells us it must be positive 1/3. What is that? A sub n is greater than 0 for all n. So, and that's thrown in there for that exact reason, because otherwise you would have 2 answers there. Okay. That would still, though, even if it's plus or minus 1/3, we would still be able to say for sure that the series does what? Converges, right? Whether it's positive or negative, because we're taking the absolute value of that 1/3 is less than 1, so the series converges. Okay. And then we can say, well, then the sum from n equals 1 to infinity of a sub n is equal to the first term, 720, over 1 minus the 1/3. Okay, which I guess we can multiply 3 here. So what is that? Goodness, it's 2,160 over 3 minus 1. So 2,160 divided by 2 is 1,080. Okay, and so there's where it converges to. Okay. Beep, 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 beep. All right, we'll stop there. I'm not going to keep going with that.
Sweet.
All right, because the next one's kind of long, and I'll stop there. All right, so we'll get to that next part on Monday. We'll finish up this section on Monday. Okay? Yep.
Can I go to that with Mike?
Only if you promise to hold hands and skip down the hallway.
Yes.
Mike and I definitely didn't want to do that.
No, yeah, you may go, Mario. Yeah, go ahead.
Mike, you left my car.
Okay, so I will post